I'm Adam from RFOXiA, from our real lab. Today we're answering why did nothing useful exist between a $5 consumer BLE chip and a $5,000 military radio until now. Let me describe the wireless market the way it actually existed for most of the last decade and a half. On one end you had commodity BLE modules, the kind that ship inside fitness trackers, wireless earbuds, and smart light bulbs. They cost between $5 and $15. They reach about 80 to 100 meters under ideal conditions. They are adequate for the applications they were designed for, which are applications where you are in the same room as the thing you are communicating with. That is the bottom of the market. On the other end, you had military and industrial long-range RF systems, units from companies that supply defense contractors and governments, systems capable of 150 kilometers of range, encrypted links, interference resistance, the full package. They cost between $5,000 and $50,000 per unit. They require licensing, they require training, they require a procurement process that most independent builders will never navigate. That is the top of the market. Now here is the part that should bother you. Between those two things there was almost nothing. Not a little bit less than military grade, not a meaningfully improved version of commodity BLE. Almost nothing. The gap between 100 meters and 150 kilometers was, for the most part, commercially unoccupied. And the reason for that is somewhat absurd when you examine it. The wireless industry is obsessed with transmission power. The accepted engineering logic for decades has been that if you want more range, you need more power. Bigger amplifiers, higher wattage, more antenna gain, shout louder. That logic is not wrong in isolation. More transmission power does increase range, but it also increases power consumption, which matters enormously for battery-operated systems. It increases regulatory complexity, because high-power transmitters in unlicensed spectrum attract regulatory attention. It increases cost, because RF power amplifiers are not cheap. And it increases heat, which is a genuine engineering problem in small form factors. So when manufacturers looked at the space between a $5 BLE chip and a $5,000 military radio, they concluded that filling that gap would require expensive amplification, complex RF design, regulatory headaches, and the result would still cost several $100s or more before anyone had built a complete system around it. They decided it was too expensive to solve for the market that actually needed it. Students, drone builders, field researchers, IoT developers, independent engineers, the builders. And so the gap stayed empty. What I did differently was ask a different question. Instead of asking how to transmit more powerfully, I asked how to receive more sensitively. Receiver sensitivity is measured in dBm. It describes the weakest signal your radio can still detect and decode. A commodity BLE chip typically has a receiver sensitivity around -90 to -95 dBm. That number and the amplification logic baked into the industry's assumptions is why everyone kept building louder transmitters instead of better listeners. The chip at the core of the Multinav Pro Plus BLE module has a receiver sensitivity of -104 dBm. That is not a marginal improvement. Every 3 dBm of additional sensitivity roughly doubles effective range. We are talking about nearly 10 dBm of improvement over commodity chips. That single design decision, selecting for receiver sensitivity rather than transmission power, is what makes 20-kilometer man-to-drone range achievable on standard unlicensed Bluetooth spectrum, without the amplification costs, without the power penalty, without the regulatory complexity. The physics was always there. The question was just being asked incorrectly. The result is a module that sits precisely in the gap that the industry decided was too inconvenient to fill. 5-kilometer ground-to-ground range, 20-kilometer man-to-drone range, 50-kilometer drone-to-drone range where ground reflections are eliminated. That is the engineering logic behind why the gap existed and how the receiver sensitivity approach closes it. Now let me show you the actual hardware. This is what closing a 20-kilometer market gap looks like in hardware form. 2 of these modules paired together reach 50 kilometers drone to drone. No towers, no internet, no licensing, just unlicensed Bluetooth spectrum used correctly. 2 megabits per second over that distance. This is not a slow telemetry link for occasional sensor pings. This is a data rate sufficient for real-time control, live sensor streaming, and responsive feedback loops on fast-moving platforms. The STM32WB07CV6 is doing 2 jobs simultaneously, managing the BLE stack and running your application firmware. A single chip handling both means lower latency, tighter timing, and no interprocessor communication overhead slowing things down. 57 by 47 millimeters, that is smaller than a standard business card. The antenna wire extends 140 millimeters. This fits inside a racing drone frame, a field sensor enclosure, or a handheld device without forcing compromises in the mechanical design. The module was designed from the start as part of a system, not a standalone component. The GNSS module, the sensors module, and the motor and battery management board all connect to defined interfaces on this board. One platform, multiple configurations. The RFOXiA Connect app gives you a PS5 style controller interface, a live map with GPS overlay, and real-time sensor data, all over the BLE link with no internet connection required. The range of the app is determined by the range of the module, which is up to 20 kilometers. When two people both carry a Multinav Pro Plus module, they can exchange text, data, and voice completely off-grid. No cellular signal, no Wi-Fi, no infrastructure of any kind. This is the same hardware running a communication network and a control system simultaneously. Full source code access, SWD programming interface on board. If the default firmware does not match your application, you rewrite it. The module does not lock you into a proprietary ecosystem. The AI firmware builder in RFOXiA Club can generate production-ready custom firmware from a plain language description. The RTC crystal is a detail that matters when your system depends on synchronized timestamps, sensor fusion, coordinated multi-node logging, timestamped navigation data. Precise timing is built in, not added as an afterthought through an external component. 2 megabits per second data rate, FCC certified, $59 for 2 units. The military did not need to solve this problem. The commodity BLE manufacturers had no incentive to solve it. Nobody was building for the person who needed more than 100 meters but could not spend $5,000. So I built it. The Multinav Pro Plus BLE module fills the uncontested middle ground between toy-grade BLE and military-grade RF, giving serious developers professional range wireless hardware at a price that makes sense.